Okay, so in the previous video, we did a little bit of a calculation, which was looking at how the elastic potential energy can turn into kinetic energy. So, example was you take a spring and you fire a ball bearing, and we work out the velocity of the ball bearing. Now, in that calculation, we talked about the equation, which was for elastic potential energy. This elastic potential energy equals half Ke squared. Okay, now in that we had this thing here, K, which we call the spring constant. We have another equation as well, F equals Ke. Again, we'll get to that in a later video, but again in there we've got this thing K, the spring constant. So a lot of questions we get is, well, what does this mean? What is the spring constant? Well, if we take this second equation and just focus on this one, if we rearrange that to make K the subject, K equals F over E, where F is a force that we are applying to a spring, measured in newtons, and E is the extension or compression of a spring, which we measure in meters. So that gives us newtons per meter as our units for spring constant. Right, well, what does that mean? Well, if you think about what those units are, it means the amount of force needed to get an amount of extension of a spring. It's effectively saying how tough is it to stretch the spring or compress the spring. So we've got two springs here. This first spring, like the ones we use in lessons, does not require a lot of force to extend that spring. So it's going to have a fairly low spring constant. Okay, not much force necessary to give you 1 meter. I mean, if I stretch that to a meter in length, it's really not requiring much force for me to stretch that. So it's a fairly low spring constant. This spring, it's a tougher spring, okay, different shape. I mean, springs all have different sizes and shapes, but crucially, more force is necessary for me to extend that spring. So it's going to have a higher spring constant. More force, newtons, needed per 1 meter of extension. If I stretch this one to a meter, it's going to require more force for me to stretch that to a meter than that one. So we can look at it like this. If that first spring required 1 newton of force to extend by 1 meter, 1 newton divided by 1 meter, okay, this gives you 1 newton per meter. That's its spring constant, 1 newton per meter. Okay, if this one requires, 10 newtons per 1 meter of extension, that's going to be 10 newtons per meter as the spring constant. Okay, and that just applies to any spring that we have now. Right, so a spring that you measured is requiring 5 newtons of force to stretch 20 centimeters, or 5 newtons per 20 centimeters is 0.2 meters. 5 over 0.2 is going to give you 25 newtons per meter.